One, two, three.
Right, okay. Welcome everybody. Good evening to this next session on the practical workshops. This is part number 3. And tonight we're going to be looking at some dark coloured minerals. So what I want to do, just a quick recap from last time. Then I want to try and bring some sense of order to what we've been doing. And then we'll come on to the dark coloured minerals. Now, it might have been apparent to you that what is happening over these few weeks is that each week is getting a little bit more complex than the week before, and this is intentional. It's to start you off in a simple way and to build you up to slightly more complex issues. And so it continues to get a little bit more complicated, or not exactly complicated, but a little bit more material to take in each time. This is, as I say, this is number 3, and we're going to be increasing the some of the concepts, particularly in terms of the minerals that we're looking at and what their significance is. But before we go into the greater detail, what did we do last time? Well, we remember that the things we looked at to help us identify minerals, things like the crystalline nature, particularly the crystal habit, which is really the shape of the crystals. Color can be quite an informative guide, but not a unique guide to minerals. The property of luster, how shiny they are or otherwise, whether they are transparent, translucent or opaque, and a property we call the diaphaneity. The cleavage, whether they've got cleavage or not, particularly any associations of a mineral with other minerals that you might have identified within the rock. And what I mean by that are things like recognizing or thinking you've recognized olivine, for example, and thinking you've recognized quartz in the same rock. Now, the association of things like olivine and quartz don't normally happen. And so if you do find yourself with quartz and olivine, maybe one of them's wrong and you need to rethink. So that's what I mean by associations, and we'll be talking about going to associations in a little bit more detail. So what did we do last time? Well, we looked at the alkali feldspars, and we also looked at white micas. And when we were talking about the alkali feldspars, and this was a bit of a recap from the first week, that these particular shaped crystals, what we call lath-shaped crystals, those were definitive in being able to identify alkali feldspars and in plagioclase feldspars as well. So the alkali feldspars that we looked at last time, well, they had that lath-shaped crystal. They were euhedral generally, but they could be sort of slightly poorly formed and not with particularly good crystal shape, but often they were nicely crystal shaped in those lath shapes. And for the alkali feldspars, they were generally opaque rather than translucent like the plagioclases. So the alkali feldspars are generally opaque and in colors of white, pink, brown, pale red, or gray. And if you remember, I said the only color rule that you can give realistically to feldspars is the one that says plagioclase is never pink. So if you've got something pink and you've identified it as a feldspar, then it's an alkali feldspar. The other properties that the alkali feldspars, along with the plagioclases, share is the satin luster. So it's a slightly less vitreous, it's that satin finish luster. And for the alkali feldspars, they will show simple twinning, and you can identify this by looking at how the light is reflecting across the mineral's surface. And if you've got a simple twin, one half of the crystal will reflect light differently to the other half, and so that's how you would determine that you've got a simple twin. If you've got complex twinning, as you find in plagioclases, then you will see each of those individual lamellae reflecting in a different way. So they're somewhat more complicated to pick out in hand specimen. So those are the alkali feldspars. Then we looked at white micas, and the white micas, as the name implies, light colored, very silvery, probably one of the characteristic features of the white micas. Transparent to translucent, very, very shiny, metallic or plastic, glossy luster. And generally they occur, pieces of white mica will occur as thin flecks and flakes. Or if you've got a lot, you get sheets, what we call books of micas, because they look like a book looking at it end on. And the sheets are really the cleavage planes of the individual sheets of the mica. Now, these are hexagonal in their crystal system, but it's very rare that you're able to actually identify the proper hexagonal shape of the mica crystals. The other thing about them is that they are quite soft and flexible. Now, we can put this detail here into a better format. Now we're building up our inventory of properties, and they're almost getting out of hand. So we can become a little bit more ordered now in our recording of our qualities and characteristics. So all I've done here is just to lay out those various properties that we've just mentioned along here, and we then list those various properties for the various minerals. And this first row is the alkali feldspar row. The second one is the mica, the white mica row. So that's now putting in a little bit more order into all this information that we are beginning to accrue in terms of the properties of these various minerals. And of course, as we develop the number of minerals that we know about, then this list is going to get longer. And what I will do at the end of the whole session is I will send out, or it will be sent out, the complete list in this format for all the minerals that we've discussed in these sessions. So that will come out as a handout at the end. So you'll have that for future reference. Right, let's now start off with what we're up to this evening, the dark minerals. And the first group of dark minerals that I want to talk about, it says there, it's the pyroxenes. And these are a major group of rock-forming minerals. And we class the pyroxenes in what we call the ferromagnesian minerals. And that name should really tell you what they are really composed of, and that is that they are made of iron and magnesium. Those are the two dominant cations within the crystal structure. And where these minerals are most common is in the basaltic, in the mafic rocks and the ultramafic rocks. So these are the minerals that go to form the things like the peridotites, the gabbros, and basalts, and so forth. And as you come into the more intermediate rock types, the pyroxenes become less apparent. And as you come into the felsic rocks, the silica-rich rocks, pyroxenes play a very, very minor role, if any at all. So the pyroxenes, these are the major group of ferromagnesian minerals to look at. And we've got two sorts, and the sorts are dependent on the crystal form, the crystal system that they fit into. We have a series of pyroxenes in the orthorhombic crystal system, which we call the orthopyroxenes, and we abbreviate that to OPX, and that's orthopyroxene. And these are the minerals that are generally regarded as enstatite and or hypersthene. Now, enstatite is the magnesium-rich end member. Hypersthene is the sort of the bit in the middle, which has got about the same amount of magnesium as iron within its structure. The iron-rich end member, something called ferrocylite, is not very common at all, but you can find enstatite. It is in some various rock types, so we will find some of that. If anybody can remember my field trip to Cyprus, the virtual field trip that I did a while ago, there were some pyroxenite veins. Well, the light colored veins were made of this enstatite orthopyroxene. Not a major group, but as I say, it is there. By far the most numerous of the pyroxenes are the clinopyroxenes, which fit into the monoclinic crystal system. We abbreviate these to CPX. And of these, the common ones that you probably come across are things like augite, and this one called diopside. Those are the two common ones. Now, if you're out in the field, you can't tell the difference between orthopyroxene and clinopyroxene in the field. So it might be color for enstatite. The light color might be the giveaway for that, but for the rest of them, you can't do it. Right, so that's a little rundown of what the pyroxenes are and their significance. As I say, in terms of a basaltic rock, a gabbro, for example, something like that, pyroxenes make up a good 40%, maybe 50% of the mineral complement, with the plagioclases forming the majority of the rest of the composition. So they are significant minerals in igneous rocks. Right, let's start our tour of some of these pyroxenes. The crystal shape, these are usually quite stumpy, what we call stumpy. So they are sort of elongate, but they're squat. Squat and stumpy is the term we generally give to these pyroxene crystals. And the color, well, you can see the color of this one. It's this nice, almost black. It's a very deep green, dark green in these cleavage fragments on this end of the crystal. Quite glossy, reasonable luster, slightly vitreous to maybe subvitreous. Certainly no way as glossy as the micas that we looked at last week. So subvitreous would fit quite nicely into the terminology for this mineral. The other thing to notice is these lines. You see all these lines along here, lines down there, there's lines up there. All these lines along, these are all the cleavage planes. Look, all these ones along here, these are all cleavage planes. And pyroxenes have this longitudinal cleavage. There's also a set of cleavages at about 90 degrees. It's not exactly 90 degrees, but you wouldn't know that just by looking. And here are some of these 90-degree ones here and across there. This was one originally before it got filled with some alteration mineral in there. So when you're looking at pyroxenes, looking for the cleavage is a good thing to do, because these are the cleavages are well developed, generally speaking, on pyroxenes. Now, if you had a basal section, and the basal section, you'd be looking into this end, really. There you will see the two cleavages intersecting at about 90 degrees. As I say, it's not exactly 90 degrees, but it's as near as, damn it, 90 degrees. And so if you happen to get a basal section in your rock, you'll get you could get a 90-degree cleavage intersection developed. Right, so that's a nice stumpy black dark green crystal of pyroxene. There's some pyroxene in a rock. This is a black variety. There's our scale bar down there. That's a centimeter. So these are quite big, well-shaped, prismatic is another name we give to these crystals. Prismatic, but they are stumpy. They're not elongate. They're sort of squat. There's a nice one there, black. Some smaller ones in there. There's one there. There's one there. which may be showing its cleavages. In fact, that is showing its cleavages in there. So that's a nice one there. Next door to something that you will instantly recognize, having done this in the first week. If I can find my pointer. This is, of course, is plagioclase, that translucent to transparent, light-colored feldspar. That's plagioclase. These are our pyroxenes, so nice stumpy, black, subvitreous luster crystals. There's another one there. There's our scale bar. That's a 1 centimeter scale. There's a nice one there. So these are slightly more, possibly a little bit more brown, browny black, dark anyway. There's a good one there. And again, this one, I've just looked at this, just there, it's showing its cleavage there, just along there, up in there. There's another nice one in there. There's one there. There's one there. And yeah, so again, this rock here, got plenty of these nice squat, stumpy pyroxene crystals. Right, let's go on. There's another one here, and again, there, all these black pieces. They're all, this is all black pyroxene, little stumpy crystals. And that's sort of subvitreous, not, they don't shine and burst out at you, they're a little bit more subdued. So these are all pyroxenes. There's another one here, nice plagioclase up there. There's your scale bar. And again, oh, that's a basal section there, that one there, I've just noticed this. Can't see any cleavage on it though. But these squat, stumpy, slightly paler possibly, crystals here. So these are all nice examples of pyroxene. These ones here, in there. So those are nice pyroxenes. Now, on this one, this is quite a coarse grained variety. There's our scale bar there, that's a centimeter. So these are quite big, 2 to 3 centimeter crystals of pyroxene. Dark, very, very dark green, almost black, but just about see the greeny tinge on some of these, possibly in that one. But the thing about these is that all the cleavage planes, you see, they're all the cleavage planes are well developed within here. Some in there, along there, in there, and all in here, up there. There's a possible 90-degree one across there. And this piece, you see, look at all those cleavages down there, all down there. So quite nice development of cleavage. But again, that sort of stumpy appearance, more squat. And put that one there, that's squat, and that one there, and that one there. I think there might be a bigger one. Yes, there's a bigger one here. You can look at these cleavages in a bit more detail. There's the, it's up to 2 centimeters now. There we've got the cleavages nicely developed in that piece. Again, squat, stumpy, subvitreous luster, very, very dark green. Along there, we've got the cleavages on there. Here, they're everywhere. In fact, these are flakes that are flaking off. These are cleavage flakes that are just breaking off the main surface. And of course, that's how things break up. It's along cleavage planes that they break. And there's all the cleavage planes along there. And of course, the cleavage planes are directly related to how the atoms are arranged within the crystal lattice, which is what cleavage is. You know, planes of different atoms and so forth. Right, so those are the characteristics of these pyroxenes. So generally very dark, dark minerals. And there's your millimeter, these are millimeters down here, this is a millimeter scale. Here we've got Nice basal section. I can see one set of cleavages. I can't make out any, the other one at 90 degrees. It's another basal section there. There's a stumpy bit there, and stumpy one there. Various stumpy bits. This is in a finer grained matrix, so this is a porphyritic. Remember that texture we talked about either last week or the week before, where we have larger crystals, what we call phenocrysts, within a finer grained ground mass. And these are the pyroxene phenocrysts. There's another one there. So quite characteristic in this dark color, stumpy crystals, and they're not excessively glossy. They're more subvitreous in their luster, and not very, they're translucent to opaque, more generally translucent to opaque, more on the opaque rather than the translucent. So summary here. So prismatic stumpy crystal, and generally quite often good shape, dark brown, greeny brown, black. The glossy luster, sometimes subvitreous, yeah, but not as glossy as micas, and certainly doesn't leap out at you like micas do. And the longitudinal cleavage and the 90-degree one, if you've got a basal section, you will see these two intersecting on, or you can see them on those basal sections. So that's the summary of these pyroxenes. Now, if we can put that data into, oh, sorry, I've forgotten about this one. How do we know this one is a pyroxene? Well, you've got cleavage here. It's certainly not a color that we've come across so far, but there's cleavage there, and here's a piece here, and there's cleavage on this piece, and that's a sort of stumpy squat crystal. That's another face of one. That's a stumpy squat crystal, and that's quite stumpy and squat, and that's stumpy and squat there and there. Some there. There's a slightly less green one, but this brilliant, and there's more cleavage in there as well. Now, this brilliant green color. I think there's a bigger one. Yeah, that's yeah. So here we've got more green. Now this is slightly more translucent than the pyroxenes we've just looked at, and particularly this piece here, where we've got cleavages running down in this direction, and we've got them going across there as well. So there's our 90-degree cleavage. In fact, there's more you look at these, the more you see cleavage in these pyroxenes. I think that's another piece there. There's certainly cleavage planes in that direction along there. But these green pyroxenes, this is the pyroxene diopside. And as soon as you see something which has this bright green color, it's often called an apple green color. Whenever you see a mineral that is bright green, there aren't too many minerals that are bright green and have got pretty good crystal shape and cleavage, as this one does. So if all those three qualities come together in your mineral, then you're likely to have diopside. And diopside is the calcium rich. You can have, as it says here, you can have a chromium rich variety of diopside, which is even brighter green. But the characteristics of diopside, just like the pyroxenes, because they are a pyroxene, it's just another pyroxene, but a calcium rich pyroxene, they have this prismatic stumpy nature, often good crystal shape. We talked about the color, glossy luster, but it can be this subvitreous. It's certainly not as shiny. It doesn't leap out at you like the micas and some other minerals that we're going to see shortly. Transparent, translucent, particularly for the diopside, verging on opaque. But remember, as I say, diopside tends to be more in the transparent, translucent rather than the opaque. And we've got the cleavage, talked about the cleavage, we've seen the cleavage. And if you've got those basal sections, then you've got two intersecting cleavages on those basal sections if the cleavages are well visible. So those are the pyroxenes. And we can put these now into our developing table of qualities of rocks. And remember, I will give out the complete list in this format at the end of the series of talks. So we've just stuck all the stuff that I've just talked about into these headings here. So stumpy prismatic euhedral, these are nice crystals. Translucent, yeah, slightly translucent for the augite type pyroxenes, for example. Glossy to subvitreous. There's our longitudinal and 90-degree basal cleavage, and that's that range of colors. Don't have any twinning. When we come onto the pyroxene diopside, the slightly more transparent to translucent, and it's this green, apple green and bright green colors that is the giveaway for diopside. So you should not be forgiven for mistaking diopside. Remember, the other green mineral that you've come across so far is olivine, and of course the thing about olivine is it doesn't have stumpy prismatic euhedral crystals, generally speaking. So you won't mistake one for the other. Right, so those are the pyroxenes. As I say, that was a major group of the ferromagnesian minerals. We now come on to another of the major classes of rock-forming minerals, ferromagnesian minerals, and these are the amphiboles. Now, the thing about the amphiboles, if you remember what I said about the pyroxenes, I said that they were the predominant minerals in the mafic and ultramafic rock types. When we come on to the amphiboles, you do find amphiboles in the mafic and ultramafic rocks. They are less common in the mafic and ultramafics, but they occur much more commonly in the intermediate rock types, the diorites and the andesites, things like that. So these are, as it says, these are less mafic, if you like. And technically what that really means is that they do have less iron and magnesium in their structure than do the pyroxenes. And they have less iron and magnesium because there are lots more other elements within the amphiboles. There's more silica and there's more aluminium, and there's also some OH in places. So these minerals form in a less anhydrous setting. You remember your ultramafic rocks, your ultramafic magmas, your mafic magmas are those that are very, very, very low in water. So those are, we regard those as being anhydrous magmas, whereas the magmas that go to form the intermediate rocks like diorites and andesites, for example, cyanites as well, those have slightly more water in their structure, only slightly more, but you do not call those magmas anhydrous. They are more hydrous magmas, and it is the hydrous magmas within which the amphiboles are found, and because they have some OH in their structure. But they are ferromagnesian minerals nonetheless. So let's start to look at our amphiboles. There's our scale bar, that's our 2 centimeter scale bar. And well, I think the thing to look at first is comparison with what we've just looked at with the pyroxenes. You remember the pyroxenes had those squat, stumpy crystals. Well, look at these. These are all these elongated, bladed, like carving knife blades. They are also needle-like. There's no needles in this one, but the term acicular, meaning needles. So bladed, elongate, and acicular are names that we would give to the crystal form of amphiboles. And the color, well, you can see the color here, it's this dark green color. All these lightish bits are where light is reflecting. So that says these are more glossy, their luster is higher than that of the pyroxenes. And this is one good way to start distinguishing between the two. If you've got two black minerals, one of which is stumpy and subvitreous in its luster, and the other one which is elongate and quite glossy, then the first one is likely to be the pyroxene and the latter one is likely to be the amphibole. So there is cleavage, there's longitudinal cleavage, and all these blades in here have got cleavage. I can find my, where's my pointer? Right, all along here, you see all those light, that's all cleavage. So all these blades, all these bladed crystals, elongate crystals, are all showing cleavage in there and all in there. So that's an amphibole. Now I mentioned the needles here, all these black and dark green needles, these are all amphiboles, all there. All these elongate acicular crystals in this rock, these are all, this is all amphibole. So all this stuff here, so this is all amphibole in there. So all this stuff is amphibole. So one giveaway for the identification is this: if you happen to have the needle variety and the thin blades, there's a thin blade there, then that's quite a giveaway for the amphiboles. Now this is full of needles. You look at your scale bar, that's your 1 centimeter scale bar, but you start to get your eye in, it's full of 2 to 3 millimeter long black needles. It's full of black needles everywhere. Look, all the black needles everywhere, full of black needles. So this rock, it has, well, at least 50% of this rock is amphibole in these black needles. This is just full of amphibole up here and just along there. This is a slightly higher mag. There's your 1 centimeter scale bar here, and you see there's just these needles everywhere, black needles. Now I think you might be able to see from here that because these needles are standing out, it means they are, well, they're quite glossy. They're noticeable because they have this gloss to them. And the more you look at them, the more you can start to see this gloss on them. They are very glossy, far glossier than would be the pyroxenes. So all these needles, all those things there, up in here. So all those, they might be small, but they're all needles and they're all glossy amphiboles. Something slightly coarser grained, that's a millimeter scale along there, that's a millimeter. And again, you see we've got these needles, slightly more bladed rather than needles here, but black, reflecting the light, some there. And again, this rock here has a high proportion of amphibole in it there. All this stuff here, this is all amphibole. So all the black, all these black elongated crystals, this is all amphibole in there. Now, if you get so much amphibole that, well, there's just nothing else, you can call the rock an amphiboleite. In fact, that's what we do call them, only we call them amphibolites. And strictly speaking, we've crossed over into the metamorphic area, and I wasn't going to do metamorphic rocks until quite late on in the series. The last one is going to be on metamorphic rocks, but regardless of what this rock is, it is composed completely of the mineral amphibole. And when you get so much amphibole, it starts to take on quite large crystals. But the crystals are quite different to the pyroxene crystals because they are very, very black and very, very shiny. All these ones in here, you could, if you weren't careful and you didn't look at the color, mistake these for mica. They are that glossy. But this whole thing, look at the overall green color of this. You're looking at loads and loads and loads of little needles, or quite big needles actually, all lined up with each other. And then these larger areas of bigger amphibole within the rock. There we've got some more shiny, quite definitely shiny, and all this stuff here is just reflecting. So very, very glossy. And again, it's this glossy character that gives away the amphibole. Here you can see some cleavage in there as well. You see there's longitudinal cleavage in there on this piece here, longitudinal cleavage on there and in that one. One of the things about doing all this investigation is something that you'll all have come across time and time again. You know, I'll say, Carl says, it's getting your eye in. Spend some time just having a tour over the specimen that you're looking at. You get your hand lens out, just look over it and begin to take in what's there. And the more I'm seeing cleavage all over here now. See all this stuff along here. Look, cleavage in there, cleavage up there. It's just full of cleavage, some stuff going that way here. So take plenty of time when you're looking at these things, and more features will leap out at you. So that's quite coarse amphibole in this one. So summarizing the amphiboles, well, we've got these long bladed, elongate prismatic needles, and acicular is the term. They can be a little bit more squat, but you won't confuse them, you shouldn't confuse them with pyroxenes because of this very glossy luster, very, very glossy. They are not particularly transparent. They're mainly the translucent and more generally the opaque. And the color range is usually these greens, dark green, brown, black, or even black. And we've seen these longitudinal cleavages. Now, if you are lucky enough to get a basal section, you do get intersecting cleavages, but they form 120, again, it's not 120 degrees, they will appear to be 120 degree intersecting cleavage on the basal sections. But firstly, you have to have basal section, and secondly, you have to have the cleavage visible, because it's not always visible. It will be there, but you don't necessarily see it. And if you do have this unequivocal 120 degree cleavage, then that is the hallmark of the amphiboles, and that's the hallmark of the crystal structure. Now, these are these general, we use the term hornblende. Strictly speaking, hornblende has got its own chemical identity, so it is a mineral in its own right, and you won't know the chemical identity of what you're looking at unless your eyes are very adept at X-ray analysis and so forth. So you should technically call the stuff that you identify here as amphibole, but we tend to use the term hornblende really meaning, oh, it's just amphibole, which technically isn't correct, but that's general practice. So, you know, you do what you want, but remember it's either one or t'other. An amphibole is strictly its proper name. Now, bladed crystals. acicular, lots of acicular stuff in here, blades, lots of blades. Ignore this, there's all this pale green stuff. This is just chlorite alteration, forget that, ignore that. It's all this stuff down here, these, all this bladed, quite glossy, it's reflecting the light, particularly in here, quite reflective, glossy, needles and blades. Look at the blades up here, full of bladed crystals. So looking at purely the crystal habit, you would, well, you ought to classify this as an amphibole. And with the cleavage that I'm going along here, it's this longitudinal cleavage. So again, that should really reinforce your identification of this mineral as an amphibole, which would be correct. It's opaque. Well, we said, yeah, they can be opaque. But the thing about this is the color. And this particularly down here, and unfortunately the photography, the camera processing, the film processing onto the PowerPoint slide and the Zoom presentation is degrading the color. But certainly on my screen, what I'm looking at around my pointer here is a deep indigo blue color. And if you're not seeing that, well, you should be seeing it. So all the stuff around here is, or should be, deep indigo blue. All this up here is deep indigo blue. All this stuff within the chlorite, which is pale green, all this stuff here is deep indigo blue. And I put this in here purely because if you do happen to find something that fits all the properties that you expect from an amphibole, but it has a deep indigo blue color, you are looking at an amphibole, but it's a very, very, very special sort of amphibole. It's something called glaucophane. And the reason it's very, very special is, and again, I am transgressing what I said I was going to do and leaving metamorphic rocks to the end of the series, but glaucophane is a major component of a particular metamorphic grade, what we call a metamorphic facies. When we are altering rocks by pressure and temperature, we call these changes in the rocks, they go up in, well, not a series of steps, but we use what are called indicator minerals to give us an idea of the sort of temperatures and pressures that the parent rock has experienced to take it up to the metamorphic grade that we now observe. And glaucophane is one of those marker minerals. And glaucophane gives its name to the glaucophane metamorphic grade, the glaucophane facies, or because this is blue and the arrangement of all the cleavage planes in these blades looks rather like schist, the metamorphic facies is blue schist facies. It's quite a high temperature and high pressure facies. But the presence of this mineral, this amphibole glaucophane, is that identifying mineral for the blue schist facies metamorphic grade of rock. And this is glaucophane. And since we're talking about amphiboles, I think it fits properly in here. I will say more about the metamorphic minerals in the last of the series. Some more metamorphic minerals that are relatively common. So this is glaucophane. So we can now look at the properties. Well, all the properties that we've talked about for the other amphiboles, just the same, except that it is, well, it says there's translucent. It is more on the opaque side than translucent, but this is the giveaway. It is this deep indigo blue color, and it's the only amphibole that has that deep indigo blue color. So now let's put together our amphiboles. Here we've got the acicular bladed, as well, fits for both of them, translucent to opaque. So some of the hornblende type of amphiboles can be slightly more transparent, but for the glaucophanes, I say opaque is the more common form. Very glossy, plastic to vitreous, so very shiny, leap out at you. They're so glossy. The longitudinal cleavage and the 120 degrees on the basal is the amphibole indicator. And the color for your hornblende type or your ordinary amphiboles, black to dark brown, dark green to pale green at times, less common in the pale green form. But when you're in your glaucophane amphibole, then it is that deep indigo blue color. So those are the amphiboles. So we now covered 2 of those dark minerals, and as I say, those 2 that we've covered are a significant component of many igneous rocks. The last group of dark minerals I'm covering tonight are the minerals that are more common in the more felsic rocks. And that's because as we come into the micas, and that's what these dark minerals here are, the micas have more water in their structure. So these will form under more hydrated magmas. You won't find these very commonly in anhydrous magmas, or at least not some of these micas. So what can we see about the micas? Well, first of all, let's look at our scale bar. There's our scale bar, so that's 1 centimeter. And it's these dark, since we're talking about dark minerals, let's look at these dark ones. It's these pieces here, these black flecks, quite shiny. If you look up here, they're quite shiny. Shiny bits up here, shiny. All this is shiny. All these bits are shiny. So it's black and shiny. Flecks and flakes. Probably a couple of millimeters size, these things that we're pointing out here. So little tiny flecks, little tiny flakes of the mineral mica. All these ones there. And that is in a ground mass which is dominated by, well, you'll know what that is now, vitreous, glassy, no crystal shape, grey to transparent, got to be quartz. And if this is pinky brown and it's got lath-shaped crystals like that one, then that's got to be an alkali feldspar because it's got a satin luster on it. So this is a sort of granite that we're looking at here. But the black flecks are this particular mica that we're examining at the moment. Glossy, shiny, and little flakes of it. There's our scale bar down there, that's 1 centimeter. And again, you can see here all the glossy little flakes of mica, flecks of mica. This is, we're looking at an end-on one here, and it's shiny. It almost looks like a white mica. It isn't a white mica. It is a dark mica, but it's light color because the light's reflecting off it. We're not seeing its true color, but we are seeing this basal cleavage on it. It's splitting into sheets. That's what they do. But there's more of the black around there. So this is all this there, all that. This is all this black mica. And dark mica, black mica. Biotite is the general one, but again, biotite, we tend to be quite lax in our use of the term biotite. if we find a black to dark brown mica, we would call it biotite. But remember, biotite is a chemical entity in its own right, and you can debate how accurate you were in calling it biotite rather than dark mica. Many do call it biotite when it's just a black to dark brown mica, without any further analysis. But anyway, it is black to dark brown, transparent in thin flakes. It's transparent, not so easy to see in the black, but with the dark brown you can sometimes see it is transparent. It is translucent if it's not transparent, but it's very shiny. You remember the mica that we talked about in the second session? That was this very, very glossy, what we called a metallic or a plastic glossy luster, very, very shiny. And that's this biotite mica, this dark mica. That's exactly the same here. And the occurrence will be as these thin flecks and flakes. But if we get thicker quantities of these crystals, these sheet crystals, they will look like they have this book form when you're looking at the individual cleavage sheets of the mica. It should have a hexagonal shape, but very rarely do you see the hexagonal shape. It's very soft, again, like the white mica that we looked at earlier, soft and flexible. And this one again has this perfect basal cleavage, and those books and the flakes that we saw that were building up into a few sheets of cleavage sheets. That's the basal cleavage being picked out. So this is the dark mica biotite. So remember the terminology. And we can put this into our table, our developing table. So the crystal habit is subhedral flakes, generally transparent to translucent. It's this glossy plastic luster, perfect basal cleavage, black to dark brown, and we don't have any twinning on this type of mica. Now, here's a rock, here's a scale bar, and in this area around here, I don't know whether you can see on your rendering of this image that there is a sort of bronzy tint in this area around here. Places like there and there and in there and there and there, that there is it looks rather bronzy. And here, whether you can see the slightly bronzy bit there, but this main face is just reflecting all the light. So whatever this bronzy thing is, it's reflecting the light very well. So it's likely to be a very glossy material. And if we look at a different specimen, looking at our scale bar there, here we've got bronzy faces there and other faces that are reflecting the light very well. So this is very, very glossy, but it is still flakes, little flecks and flakes, very, very shiny. And I'm wondering whether I can see any thicker crystals that would tell me that it looks rather like another mica. I can't see on that one. Here's a slightly bigger mag. There's our scale bar down there. And you see here again, yes, that's the bronzy. But reflecting very nicely. And I'm looking for sheets, possibly in there, possibly there. Those are cleavage planes on the sheets, which tells us this is another mica. But the giveaways should be, it is this very, very glossy, plastic, reflective luster, very, very reflective, but this very bronze color. Again, the color isn't coming out too well on the various things the image has gone through from being photographed, but a bronzy color. Here's a piece, another piece in there. And I think there's another one. Yeah, there we go. Got our scale bar down there. Again, this bronzy material. In fact, that might be some stuff behind. Oh no, maybe not. But all this bronzy stuff with very, very high gloss material. This is a mica, but it's not a mica that we've just talked about because it's too bronzy, and the biotype mica was black to dark brown, and this isn't black to dark brown, this is bronze, and this is the mica phlogopite. What phlogopite is, if you like, is the magnesium mica. As it says there, phlogopite mica, the magnesium mica. Let's just first of all look at the subhedral flakes is the general form of the crystal habit. If you get it thin enough, yes, it's transparent, translucent. It's got this very glossy plastic luster, shines back out at you. The cleavage is perfect basal cleavage, which is why you get these various sheets. But the giveaway thing is this pale bronze color. There's no twinning. Now, the thing about phlogopite mica, whenever you see a chemical composition that has magnesium in it, magnesium should alert you to two things. It should alert you to heat and deep, or deep heat, if you want, because magnesium, a high level of magnesium is related to deep, high temperature melting to generate magmas from which you can crystallize whatever. So the phlogopite mica is a mica, whereas I said the biotype micas were more felsic and they had water in their structures. Not so for the phlogopite varieties of mica, these magnesium micas. And these magnesium micas are much more associated not just with the mafic rocks, but with the ultramafic rocks. And in fact, that last mineral with the phlogopite mica on it, that was a piece of diopside that had come from the mantle. So that was a diopsidic piece of the mantle. There's olivine in there as well, but it wasn't particularly visible in that specimen. And phlogopite mica inhabits that type of environment as well. So it's one of the micas that you do associate with ultramafic rocks. So bear that in mind when you're looking at any specimens that have got phlogopite in. For example, it is highly unlikely, in fact, I don't know myself of any instances where you do find it, but it is highly unlikely, and I think it's probably totally unlikely that you'd find phlogopite and quartz together in the same rock, because the two inhabit totally different parts of the formation spectrum of igneous rocks. So that's phlogopite mica, but it does occur in a series of rocks which are more allied to granites. But as I say, they don't have quartz, but they are sort of like granites. They've certainly got some of the things of granites in them, but they're not felsic. That's where I'm going. They're not felsic, but they can have a sort of a granitic look to them purely because of the feldspars in them. So that's the other dark mica that we're going to consider. Right, okay, pull that together now. So where are we? Where have we got to? What have we come to? Well, if we see stumpy dark black things, and they've got cleavage along the longer axes, these stumpy black dark things, we can be more or less assured that those are pyroxenes, particularly if they are sort of subvitreous in their luster. If we've got something that's bright green and it's got some cleavage and it's sort of a luster which is sort of subvitreous, then that's likely to be diopside if you've got good crystal shape, which you generally do have with that. If you've got bladed crystals, which are dark, and ones that are more glossy than pyroxene, then these are likely to be amphiboles. And if you've got something that you recognize as an amphibole with these bladed, elongated, cleaved, thin, needly type crystals, and if it happens to be indigo blue, then you've really identified glaucophane. And if you've got these very, very glossy, shiny, black to dark brown flakes and books of cleavage sheets, if you've got more of it, then that's your dark mica, your biotite mica. And if you've got all the mica qualities, the glossiness and so forth, but it happens to be pale bronze, then that's phlogopite mica in flakes. So that's where we are, that's where we've come to. And what we're going to look at next time are some of the less common minerals, but these are ones nonetheless that you could very well come across. It just depends where you go and what you're looking at as to whether you regard them as common or less common. But these are the ones that are not as generally well represented in the spectrum of igneous rocks, generally speaking. Okay, I'll stop there and open this up for questions.